Okay, continuing with this theme of managing uh, finance and macro fiscal issues under climate hazard. We left off up here, I think. Yeah, we finished here. So let's go here and start looking at how to estimate impact of climate change on GDPs and public debt, which basically comes down to looking at the future, translating climate projections from IPCC to GDPs and public debt and so on, which obviously depend on many empirical relations with many assumptions. So you have to worry about uncertainties and so on. Whenever we are recommending decisions that are often not reversible or involve a lot of investment and soft and hard changes in structures and public lives and regulations, we have to be very careful about what we are recommending, right? Impact of climate change on GDP and public debt in two emissions scenarios. So we are going here from 2017 to 2100 when the report was written up. So we are looking at the so-called intermediate scenario, RCP 4.5, where, if you're aware, 4.5 refers to the watts per meter squared of additional forcing that will result from human activities by 2100, based on taking this pathway, which itself is a complicated thing. I have separate podcasts on RCPs and SSPs and so on that you can look up. So there is the midpoint and 90% confidence interval on either side. So you have unmitigated or business as usual scenario at RCP 8.5, which is kind of considered the worst case scenario, with 8.5 watts per meter squared additional forcing. Associated with them are CO2 concentrations, greenhouse gas concentrations, and emissions. So emissions are in gigatons and CO2 or CO2 equivalent, and then you convert them to radiative forcing, watts per meter squared. And not surprisingly, the drop in GDP is negative in both cases, but milder in the intermediate scenario and much worse, up to about 10%, 8%, or 9% in the case of business as usual, with the range being much larger here compared to here. So the uncertainty can be very large, and you can end up with minus 16%, or if you're lucky, you end up with only minus 4%. Public debt, on the other hand, goes up over time. Again, for the mild intermediate scenario, middle of the road scenario, it can be as high as 46% of the GDP, with a range here, and here it's higher with 50% and a much larger range as well by 2100. Okay. In terms of the next toolbox, identifying the impacts of climate change on GDP, although many assessments look at sectoral impacts of and adaptation options for climate change, few are economy-wide. This is directly due to the challenges of modeling all sectors and then aggregating the results into an economy-wide model without losing the complexity of the sector-level results. So when you do sectors, you have many details, and when you start to aggregate them, the details begin to get lost. So do you lose information and the aggregate economy-wide numbers you give, do they still remain meaningful, or do they lose value? So the literature on this proposes two main approaches: integrated assessment models, which I have discussed in many podcasts elsewhere, following up on initial work by Bill Nordhaus, who won the Nobel Prize for his work on climate economics. A few integrated assessment models estimate the impact of climate change on economic growth, GDP, and other economic variables. For example, the Link et al. 2019 use models based on simple damage functions, which are a very controversial thing, calibrated on sectoral studies to provide estimates in large regions to 2060, and we'll look at a figure in a minute. So damage function is something that's basically translating climate variables into disaster impacts. So there's a lot of uncertainty there. In a model, they can be used as tuning parameters or knobs that you can turn to change the answer, so that can be tricky. While these models provide useful benchmarks and can identify the channels through which climate change can affect GDP growth, for example by comparing impacts through agriculture and impacts through labor productivity, they also have limitations, as was shown in Toolbox B, with a focus on poverty that you can go back and look at. Integrated assessment models do not represent all important mechanisms. They are very coarse in space and time, so they can be doing chunks of 5 years by taking various sectors, including projections of population, energy use, and agricultural policies and practices, and so on and so forth. They are missing many important channels through which climate change can affect growth. For example, climate change may affect access to micronutrients, which would have implications on children's physical and cognitive development and future labor productivity. There is also evidence that disasters have most impact on economic growth when they create political instability or conflict. So something happens and there is an economic impact, but usually there is also political instability. One party blames the other party for the disaster and the outcomes, and then they take over, and then cascades of impacts on economic growth happen. Especially if there is political instability. However, neither of these are included in any current model. This was back in 2018, but still it's pretty much the case. So looking at projected impact of climate change on regional GDP 2010 to 2060 with such models, you can see that percentage change in regional GDP is obviously negative, and there are various regions for which these are done, and the ranges are quite significant. So this is uncertainty ranges in 2060 due to uncertainty in equilibrium climate sensitivity. I have podcasts on equilibrium climate sensitivity. Basically, this is a measure of how climate responds to changes in specifically CO2. Other greenhouse gases matter as well, of course, but unfortunately we don't know very well this number, and each model can be different in its equilibrium climate sensitivity, which means the projections are model dependent, and as greenhouse gases increase in the atmosphere, climate change response is not constant, so the sensitivity need not be constant. And we know that as well from past climate changes. We can estimate climate sensitivity by estimating the change in orbital forcing, radiative forcing, and the temperature change that is associated with that. So this is a very complicated business. Keeping all that in mind, you look at the numbers here for OECD Europe, OECD Pacific, and OECD America. Okay, Latin America, world, and rest of Europe and Asia here. That's not in OECD. And then much higher percentage change in regional GDPs occur for Middle East and North Africa, which is typically referred to as MENA, South and Southeast Asia, which are highly vulnerable to climate as well. And of course, Sub-Saharan Africa is the poster child for disasters, especially climate disasters, famines, droughts, etc. Okay, so what is the toolbox saying then? Second, and most importantly, the results depend on strong assumptions, the integrated assessment models, assumptions about sector and country adaptation capacity. Indeed, a physical change, say a rise in sea level, may or may not lead to more floods depending on whether a city regularly upgrades its flood defenses. While it's possible to model physical impacts based on physical laws, the ability of institutions, agencies, firms, and households to respond to changes in environmental conditions is more difficult to predict over the long term. So economic outcomes often depend more on hypotheses of adaptation capacity and performance than on physical climate change impacts. Finally, several papers have flagged that the response in terms of savings and investments can be important as direct climate change impacts in determining effects on growth. So this is continued toolbox 1 here. So determining effects on growth The cumulative effect of individual disasters can also lead to tipping points in the economic system, especially when disasters wreak havoc or more damage than the economy can efficiently cope with. As a result, the way the models endogenize economic growth, for example, with exogenous or endogenous technical change, and represent behaviors, for example, with optimal investment responses and perfect oversight or myopic behaviors, is critical in determining final results. The macroeconomic modeling debates are therefore also relevant for assessing the macroeconomic costs of climate change. Let's look at some empirical studies and other approaches on empirical studies here. These analyses use past changes in temperature and precipitation, such as year-to-year changes in average temperatures or more granular indices, and their measured impact on GDP or GDP growth to anticipate future impacts on climate change. So it's a kind of analog projection where you look at past impacts of temperature or precipitation, etc., on GDP change and assume a similar relation can hold for the future. So look at a figure which shows the effect of a 1 degree C increase in temperature has on GDP using such an analog approach. The strengths and weaknesses of this approach are different from those of modeling approaches. One advantage is that being based on historical data, it includes all channels of interaction between temperature and precipitation changes and GDP, if it's done very comprehensively. But it has other limitations because it uses year-to-year changes to extrapolate decadal changes. It can overestimate or underestimate the impact, so it's hard to calibrate these as well. So looking at this here, effect of a 1 degree C increase in temperature on real per capita output in percentage. This is done by IFS back in 2017. So we are looking at a percentage real per capita output. The red numbers are negative here, going up to minus 1.68. There are regions where there is no data or insignificant effect, and there are positive effects seen in many places. Obviously, if colder places like Canada and Eurasia, northern parts of UK into Norway and so on get warmer, there are going to be advantages. At sufficient warming, Siberia may again become the breadbasket of the world, growing a lot of wheat, for example. So climate change is going to leave behind winners and losers, which is already happening, but each summer now for the last few years we are seeing that even US and Europe are getting hammered by extreme events, so maybe nobody is really safe from climate change in that sense. But here is Sub-Saharan Africa, MENA, India and Southeast Asia are all incredibly vulnerable to warming in terms of drops in real per capita output. China has no data here or insignificant effect in this sense, but you can imagine that that's not the case for all these poor countries. So we have to be careful. Continuing with the toolbox, overestimating happens because adaptation options in this analog approach of using historic data to estimate future impacts with warming, like upgrading infrastructure systems are available, so adaptation options like upgrading infrastructure systems are available in the long term but not the short term. Differences between short and long term impacts and the role of adaptation to evolving climate conditions has been a topic of immense debate. This paper has shown conditions under which the economic impact of a marginal change in short-term weather is equal at first order to the impact of a marginal change in long-term climate, in which case adaptation is a second-order mechanism. However, these conditions are very restrictive. Adaptation options need to be defined over a continuum, no discrete options. You make changes in livelihoods, infrastructure, energy options, switching crops, etc. They are not some things you can go back and forth or regress and go back to old ways and so on. And local economies need to be optimally adapted to their current climate at each point in time used for the calibration. So complicated business. These assumptions appear unrealistic in the context of rapidly evolving climate, so there may be a significant gap between short and long-term impacts. In efforts to explore the impacts of long-term changes in climate conditions, other authors have applied econometric techniques to past changes in climate over decades, 15 years in the case of Dell et al. 2012, finding impacts that are relatively similar to short-term impacts. Continuing, underestimating happens here, but it's the same thing I have. Also, this may be different. Underestimating happens because of some activities. Ecosystems and economic sectors may be able to cope with one bad year but will not be able to adjust to permanent change. So there are chronic changes and there are acute changes. So slow changes in temperature leading to some crops becoming impossible in one place versus things that can come back. Year to year changes versus drifts make a difference. Most studies also only consider temperature and precipitation, so this approach does not capture correlated or more complicated changes such as shifts in extreme events frequency and intensity. So if heat waves become more frequent, longer duration and higher intensity as well as larger area coverage, then you will have very different crop infestation problems, crop losses and yield drops and so on. Nor do they include other types of impacts such as long-term sea level rise. Finally, simultaneous changes in multiple climate variables may lead to impacts that are different from the sum of independent changes. Okay. By definition, this approach cannot include any impacts that did not already occur in the past because you are relying on historical data, which means that it does not consider some of the most worrisome climate change impacts which are emerging with crossing a threshold of warming, for example. Work in climate sciences to identify climate analogs or find a climate today that is similar to the climate expected tomorrow at a location X has concluded that many of the future climates simply do not exist today. So they are called no analog states. So you'll end up with weather and climate in a place that has not been seen before in historic records, for example. For example, even if one can find a place that has in 2020 the temperature one will find in Barcelona in 2100, it will not have the same precipitation patterns. So temperature may look similar, but precipitation may be very different with heavy rain all the time or complete dryness. Also, empirical studies cannot include the effect of unprecedented temperature levels, a possible collapse in local biodiversity and ecosystems, or reaching physiological limits when temperatures exceed certain threshold. This could be for humans, for other livestock and animals, for pollinators, and for crops as well. Figure I2 will suggest that there will be significant benefits in high latitudes, as we saw with green colors in the GDP change, but it's unclear whether the analysis captures the negative impacts such as wildfires, new forest pests in Canada and Russia, the need to retrofit infrastructure built on melting permafrost, and extreme heat waves in cities that are also expected there. So Canada just had a massive wildfire in the eastern shore, led to pollution spreading all the way down into eastern seaboard of the US, creating unbreathable air. So this is not a joke, this is reality that's already happening. So figure I2, already we looked at this one, the changes in GDPs or per capita output per degree for 1 degree C warming. Lots of negatives in the global south, including small change in Australia, which is part of the global north, but in general global north is having a positive effect, which can be a big problem in terms of cooperations on climate action or paying for the damages that are created by climate change, created by the emissions from the developed world over the historic period from industrial revolution. So I'll stop this podcast here, and then maybe we'll have 1 or 2 more podcasts to conclude this section, which, as I said, is much longer than the other ones, but it's an important one, so we will plod through this. Okay.